In this video, I'm going to show you some hands-on practice, some examples from different supervised learning algorithm examples. And the majority of these algorithms are modeled using scikit-learn, that is a Python module for machine learning built on top of SciPy and is distributed under 3-clause BSD license. And this project was started in 2017, and then since then it has been used very much widely, and it requires Python, NumPy, SciPy, joblib, and basically this is what we are using here. And I'm going to start with linear regression example, and the example uses the data that already comes with the scikit-learn or scikit-learn package that is called diabetes dataset. And basically, let me tell you something about the diabetes dataset. This dataset includes the data of 442 diabetic patients that are measured on 10 different baseline variables. And the variables are age, sex, BMI, that is body mass index, average blood pressure, and 6 different blood serum measurements, as well as the response of interest and quantitative measure of the disease progression 1 year after the baseline. Probably this is not something that you need to know, but it is good to know what data set you're working with, because the information of the data is not that much available on the scikit-learn tutorial page. So what we're going to use here is we are only using the first feature of the diabetes dataset because we want to illustrate a two-dimensional plot. So by no means it is a very good model, but it is only used for showcasing how to do linear regression here. And then later you could see in the plot the line, how linear regression attempts to draw a straight line which best minimizes the residual sum of squares between the observed responses in the dataset and the responses predicted by linear approximation. So let's start by importing the packages that we are interested in. We are also importing matplotlib and numpy. And from scikit-learn, we get the datasets because we want to get the diabetic dataset out of it. Linear model, we are doing linear regression model and mean square error and R2 score. So let's import our packages first. And what we are going to do next, we are going to basically define our input set and our output set. Y is the output, X is the input, and then we are choosing only one feature for the input dataset. As I said, we want to see the linear relationship. And after that, we need to divide our dataset to training and test. As I already mentioned in the previous videos, it's important to keep a portion of dataset untouched for evaluating the performance. So what we are doing is basically we are dividing both the input data and the output data, and we make sure that it's basically the same division, so we don't get the wrong data. And I'm going to do this here. And creating a linear regression object is basically as easy as putting linear model.linear regression and then fit the data, fit a model on our training data set with the output of the training data set. And the output is linear regression, so it has been done. And now it is when we move to our testing data set and we use the data that we haven't kept to make some predictions and then see how close we are to the actual value. So I do it here, and then what I'm doing, I'm going to print the error, the coefficients, and the coefficient of determination, which is the value that tells you how good your prediction is. So the closer to 1 it is, the better it is. So as you see, it is pretty low, and the reason is obvious because we only used one feature for predicting the output value, so we are losing a lot of useful information in our prediction. But as I said, it was for just the purpose of having two different dimensions, so let's see how it shows here. Now, as you see, the model tried to draw a line in the middle of the points, but we already have so many points out of this line. That is why the value is so far from 1, and it's not necessarily a good model. I mean, definitely not a good model. But it basically tells you how to do the linear regression, and you have time to play with this and try other sort of regressions than the one that we had here. The next one is basically our naive Bayes example, and again I am importing pandas, and from scikit-learn I'm getting naive Bayes, and just for the trial Gaussian naive Bayes, and the rest is like before, how to train split train and test, and then classification report and confusion metrics. And from now on until the end of this tutorial, I'm going to use this famous iris dataset that is about a flower dataset. You're going to see it now. Let me just read it. I will upload the file in the Moodle page, so you can download it from there. Oh, and you can get the link to the code and the dataset in the description box, which is the link to the GitHub page where you can get the code and the sample. What happened? Oh, I didn't import this, just talked about it. Yep. And now you can see we have the species, different types of iris flowers, and we have 4 features: sepal length, sepal width, petal length, and petal width. And this is basically a proportion of our data. What I'm going to do next is basically to replace the species type with a number so that we could predict their value. Yes. And now I am going to initialize my classifier. This is CLF is my classifier, Gaussian naive Bayes, and also I'm already doing this split out the validation dataset. And you can see that my input looks something like this, some numerical values, and the output is basically 1, 2, 3. And I'm keeping the 1/3 of the data for my test dataset. And this seed is basically just for reproducibility. So what I'm getting here with this train test split set, I'm getting the X train, X validation, Y train, and Y validation. And I'm going to evaluate the accuracy basically to show how good my model is. And now what I'm going to do next is basically I'm using the training data set to fit my model on it. Then I'm going to predict it similar basically in all other approaches. You first train the model on the training data set, you predict some values on the test data set, and then you kind of evaluate the performance. Okay. And we need to do a bit of reshaping here to perform the concatenation. And let's do this. And I'm going to show the first 10 lines of the prediction here. So the first 10 lines of the actual data set, they have been all 1, and my model has predicted them accurately as well. So how is the model performance? And I'm going to use a k-fold cross-validation here to see how good it is working with 10-fold basically. and the accuracy of model is pretty high, it's 97%. So all in all, it has been a good model. Well, of course, this dataset is a very well-behaved dataset, so you more or less expect something like that. The next example that I am having here is logistic regression, and this is what I'm importing from my scikit-learn package. And then I'm going, and if you notice, I'm using the load datasets in different forms. I'm also using different formulas for dividing my training and testing dataset. So this would give you different ways of doing the same thing. And yeah, this is the same dataset. Of course, it's a bit moved around. And then what I do, I prepare my training dataset. What I'm saying is here is that I keep all the feature values except last column, and last column is my output value or target value. So let's plot the relationship. It's just to show you how they're related to each other. So I have 3 different species, and these are more features, widths, lengths, and then you could kind of see that already from this image that the features could classify these different species. What I'm going next is the same that we did in the previous models, split the data, and I'm doing now 80-20 proportion, 80% of my data for training data set and 20% of my data for test data set. And I initialize the model, and then I do the model fit. You see, it is what we always do. We first initialize the model. Basically, what I'm saying, what I'm going to tell the code is that what is the model that I'm going to use, and then we use model fit on the X train and Y train to train the model. This is a standard approach everywhere. And basically, I did a logistic regression now. Now, again, I'm going to use this for testing. I use model predict on the test dataset, and I print the predictions. And I want to also check the precision and recall and F1 score. So these are the things that has been predicted, basically based on the input features, and the precision and recall is actually pretty spot on. So this is also a very good model, predicted everything correctly. As I said before, this is not really standard behavior everywhere. So if you build a model and you didn't get 100% accuracy, don't worry, because this is normal. And then the next model that we're going to have a look at is k nearest neighbor. And I also, from scikit-learn, import neighbors and the dataset. And iris, before in the previous examples, I used iris from a locally saved dataset, but now I want to use the iris that is coming with the scikit-learn, this is the same dataset, but just to let you know, you could find useful datasets in the scikit-learn package as well. So have a look at that, and it will help you to do some bit of practice here and there and learn more. So you don't need to really look for dataset in different many places. This is already a good place to start from. Yep, and the number of neighbors, 15, iris dataset gets loaded. And what we're doing here, I mean, in the previous examples, we basically used all features, but we want to be able to visualize. So I'm going to only get 2 first features. So what I'm doing is I'm slicing the data set to get first 4 columns as the input set and the last column for the output, which was the label of the species. And let's make some color maps. These are the colors that I'm interested in. And basically, I'm going to build an instance of the neighbor classifier here and fit the data. So as before, we initialize it, And now basically we give the number of inputs and the weights as well. And then I'm going as before model fit on this. And after that, we plot the decision boundaries, and for each of them, we're going to assign a color. So this is what is happening here. And then we put the result in the color plot. So let's see how it looks. Yeah. So as you can see here, based on how I'm defining my weights, I'm getting two different plots and three class classification. And this is how the model is classified basically. I mean, if you had used more features, you could still have done that, but then the visualization wouldn't have been as clean as what you're seeing here. The final one is a random forest example that we say is one of the best classifier out there, and I want you to pay attention to this because this is going to be what you're using in your mini project. I'm going to explain the mini project in another video in more details, but what you're going to do is to build a random forest example to predict some student's grade in a course. I'm again using the iris dataset. This is one of the widely used dataset because it is very clean and gives out good results. And then I'm getting the random forest classifier. Yeah, and I create a data frame with all 4 features. Here I'm using all 4 features. These are the features basically, and then I want to add a new column with the species. And this is what we're going to predict. Well, now we have the complete data set that we're going to use for training. And now I'm using another way for dividing my training and test data set. And the reason for that is that it is quite standard, for example, to say, I mean, the first 80% or the first 70% of the data is used for training and the rest is the testing. But the fact is that sometimes how they are located also play a role. So we want to do it randomly. We don't want to just go in a list. For example, if they are sorted dataset, then it could make some troubles. So what I'm doing here, I'm creating a new column for each row, and then I generate a random value between 0 and 1. And if the value is less than or equal to 0.75, then I set that true, otherwise I put that false, and basically this is how I'm going to distinguish between my training and testing dataset. So if it's training, if it is true, it's training. If not, it is a test dataset. And let's see. So basically here it's considered all these 5 as the data points in my training dataset. So now I'm going to create out of that, based on that final column, two different data frames, one for training and one for testing. Yeah. And now let's see how it is divided if we have a reasonable number in the testing and the training data frame. I would say that is pretty good. We have 118 observation in the training dataset and 32 in the test dataset, so I'm going to go with this division. And then I create a list of features. As you saw before, we have sepal length, sepal width, petal length, and petal widths. And since it includes the original name, I would prefer to have a digit rather than that. I'm going to use 0, 1, 2 for these 3 species, and let's see how does that look now. Yeah. So now, as you see, I have divided them. I have translated the name to some digits. And as easy as before, we initialize the random forest classifier, and then I'm going to fit the model. And now I have fit the model. Now let's make some prediction of the test dataset that we haven't touched before. This is how it has predicted. I still don't know how good they are, so let's have a look and see. The first 10 observation. So as you see, basically it says what is the probability of belonging to any of these classes. For example, these are quite clear cut, 100% here, but for this there's a bit of doubt. But it is so largely more that we could say it's the first one. So in all of them, basically, it predicted the first class. And let's see the first 5. Yeah, you see, this is the first 5 is basically the same one that is predicted. The actual ones is here with a name. And let's make a confusion matrix. I think you remember it from the previous lecture or not. But what confusion matrix does is basically tell you if you predicted something correctly. And I'm going to show you now here and explain a bit more on that. So what you are seeing here is a confusion matrix. These are the predicted labor, these are the actual species. So for Setosa and Setosa, it predicted all correctly. The only time, and for Virginica, it's always predicted correctly as well. But for versicolor, 5 times is predicted correctly, but 2 times the versicolor is predicted to be Virginica. So this is a confusion matrix, and the confusion matrix is a good way to visualizing how well your model performed. You could immediately see if every numbers is on the diagonal, and everywhere else is 0, basically it is 100%. But if not, you need to have a look and see how many times it's not predicted correctly, and you could also have these colors defined, so the darker the color, the better the prediction. And there's another interesting feature that you could use when you're doing random forest classifier. Basically, you could also understand which input feature was most important when predicting the output feature. And this is where we're going to use CLF feature importance. And as you can see here, these 2 petal lengths width, so basically sepal didn't have much to do, are the most important features in predicting the type of the species. And this is what you're also going to use in your mini project too. In the final video of this lecture, I'm going to explain the mini project that you're going to work on for the coming week. Good luck and see you in the next video.